Okay, so it says if the first square started with 2 grains of rice and doubled thereafter, or if we numbered the squares as starting with the square number 0 and ending on the square 63, then f of n is equal to 2n would be appropriate. Well, why is that? If we had I know this probably doesn't equal 64, but I'm just going to use their logic here. It says the first square started with 2 grains of rice, okay? And then if we double it, we could do 2 to the n. But this says we're going to start with 0, 1, 2, 3, 4, 5. So, okay, what they're saying is, what is 2 times 1? Well, that's going to be 2. 2 plus 2 is 4. You have to add the previous one to it to get it, okay? So then 2 squared is equal to 4. I've got to add my previous 4 to it to get my 8. And that's the reason why it works out. You have to add it to it. Here, by doing n minus 1, we don't have to. Okay. Suppose instead that the first square did not begin with a single grain of rice, but with 5 grains of rice. And then the number of grains was doubled with each successive square. Write the sequence of the numbers representing the number of grains of rice for each of the 5 squares. Well, all we would have to do is double the previous, right? So it'll be 5, 10, 20, 40, okay, 40, and 80 should be correct. Yep. Those are your first 5. We're just doubling it each time. All right. So let's go to the next page. Suppose we wanted to represent these numbers using exponents. Will we still require the use of powers of 2? Well, yes, because you're still doubling. That is the factor of doubling. You're going to start with 5, just like earlier where we started with 1 cent. Now you're just going to start with 5, and you're going to double it and call it n. Okay? And it works out, as you see there. 5 times 2 to the first power is 2. 2 times 5 is 10. 2 to the second power is 4. 4 times 5 is 20. So these all work out right here. All right, generalize the pattern in the exponential expressions into an explicit formula for the sequence. How does it compare to the formula in the case where we began with a single grain of rice on the first square? Okay. So if it was a single grain of rice, we would have to say 2 to the n minus 1 because we're not starting out with our factor, okay? The power of 2 causes the doubling effect, and the 5 represents the initial 5 grains of rice. So generalize the formula even further. Write a formula for a sequence that follows for any possible value for the number of grains of rice on the first square. Well, anytime it says generalize, you're just going to put any type of starting number. Okay, and that is equal to f of n. Okay, it doesn't matter what we start with, whether we're going to start with 8, 10, 20, half a rice grain, I don't know. Whatever you're going to start with, that's where A starts out at. Okay. What if instead of doubling the number of grains, we wanted to triple or quadruple? Okay. Well, since this is the factor talking about doubling, well, this is just going to change to tripling. And quadrupling would just be to the factor of 4. Okay? So what we're doing is, for us to generalize it, we would say A, the other factor is going to be B, that's going to be the other one that's changing. So that represents the grain of rice on the first square, the A does. B represents the factor by which the grain is going to be multiplied in each successive square. Okay, so think of this. A is the beginning. Sorry about that. I get too close to my trackpad and it goes haywire. So A is the beginning. Okay, and B is our multiplied factor. So what is it doing? Okay. Is the sequence for this formula geometric, arithmetic, or neither? Okay. Well, whenever we're talking about exponential growth, it's normally going to be referred to as geometric. Okay. Geometric growth is not simply a adding or subtracting. Okay. So for example 2, it says, let us understand the difference between f of n is equal to 2n and f of n is equal to 2 to the power of n. So here, what's the difference of just simply multiplying by n or having it as an exponential factor? Okay. Complete the table below, then graph the points n and f of n on the point. Okay. This should be pretty easy. Negative 2 times 2 is negative 4. Negative 1 times 2 is negative 2. 0, 2, 4, and 6. Hopefully we took n, plugged it in here, so we just doubled it. Same thing here. We're going to take n, plug it in here. Now, you're probably going to need a calculator for this, okay? Because you're not going to be up to date on the exponent rules that you should. There's a lot going on with exponents. You probably don't know those, and that's fine right now. You're just going to plug that into calculator. So if you plug that into your calculator, it would look something like this. 2 to that little caret of negative 2, okay? Now, I know that it's going to be, whenever you have a negative exponent, that normally is going to be make that into a fraction, and you're going to say 1 over 4, 1/4. Here it's just going to be 1 over 2. And what about this one? This is 2 to the 0 power. Remember, that's still 1. 2 to the 1 power would be 2. 2 to the 2 power would be 4. 2 to the 3 power is 8. Okay, 2 cubed is 8. Okay. Now it wants us to graph that. So we're just simply looking at n as our x. That tells us that right here. And f of n is going to be our y. So let's start right here. We have negative 2, negative 4. Negative 1, negative 2. 0, 0. 1, 2. 2, 4. And 3, 6. Okay. Now for this, let's go ahead and I'll try to draw a line down through here. Close enough. Okay. Now I'm going to change colors here so we can see it different. Let's go with this blue. Okay. So this one's going to be in blue here. We have negative 2, 1/4. So that's going to be right here. Oh, nope. That's going to be positive 1/4. Sorry about that. Negative 2, positive 1/4. negative 1, 1/2, okay, 0, 1. And you can kind of see that we're starting to go up a lot quicker. Our slope's getting a lot more pronounced here. Okay. So now we have these two shapes. Okay. Now, this says describe the change in the sequence when n is increased by 1 unit for each sequence. I got to read that one more time for me. Describe the change in each sequence when n increases by 1 unit of each sequence. Okay, so what that's going to mean is for f of n, which is whenever it's just 2n, for every increase in n by 1 unit, the value is going to increase by 1, right? So as n goes up 1, the value increases by 2 units, okay? And that is for f of n, wherein it's 2n. So it's doubling each time. It's increasing by 2 units. It's doubling, okay? For f of n, when we're talking about 2 to the n power, though, whenever we're increasing, when n goes up by 1 unit, what's happening? The value is increasing by a factor of 2. Okay? So it is having to double each time. Okay? So, and that's what that says. For the sequence, f of n, 2n increases by 1 unit, the value increases by 2 units. Okay? So as it goes up, yeah, that's exactly what it says. All right, let's keep going. So here we have a typical thickness of toilet paper is, sorry for that glitching like that. Let me hit refresh, see if it'll do better. Okay, typical thickness of toilet paper is 0.001 inch. Okay, this seems pretty thin, right? Let's see what happens when we start folding the toilet paper, or stacking the toilet paper. That's what it says. Yep, folding the toilet paper. So, how thick is the stack of toilet paper after 1 fold? Well, that would just simply be twice as much, right? Let me see here. Okay. So that would be, let's write it as our exponential form. So we would have 0.001 times 2 to the first. And that would equal 0.002. Well, after 2 folds, that's going to equal 0.004. After 3 folds, two to the third is, oh no, it doesn't even want 2 to the third. It wants 2 to the fifth, sorry. 2 to the fifth. Well, 2 to the fifth is 32, okay, which is going to be 0.032 inches. All these are inches, Okay, so it jumps significantly just in those 5 there. Write the formula for the sequence of models, the thickness of the folding paper, okay, to the end folds. Well, we basically just did that. We said F of n is equal to 0.001, and then 2 to the n power.